Assalamualaikum and hello everyone. My name is Fahrul Nazhan Syahmi and this is my presentation for MEC481 Individual Assignment 2. In this presentation, I will evaluate the concept of smart materials, focusing specifically on shape memory alloy or Nitinol. I will cover 4 main parts. First, I explain what smart materials are and why they are important. Second, I explore the structure and properties of Nitinol. Then, I provide reasons why Nitinol is suitable for future development. And finally, I share a forecast of how smart materials like Nitinol will impact industries moving forward. Smart materials are materials that can sense changes in their environment and respond accordingly. For example, they may react to heat, pressure, pH, electric or magnetic fields, and then return to their original state once the stimulus is removed. Some important properties of smart materials include responsiveness to specific triggers, reversibility of the change, durability over many cycles, and the ability to perform precise repeatable actions. Common smart materials include piezoelectric ceramics, magnetohydrological fluids, and shape memory alloys. For this presentation, I have chosen Nitinol, a well-known shape memory alloy that can remember and return to its original shape when heated. Nitinol is a combination of nickel and titanium. The name of Nitinol actually comes from Nickel-Titanium Naval Ordnance Laboratory. It is famous for two smart behaviors. First, the shape memory effect. When you deform Nitinol in its metallic state and then heat it, it returns to its original shape. Second, superelasticity. It can stretch or bend significantly and then snap back to shape when the force is removed, even without heating. These behaviors are useful in many industries. For example, in medical devices, Nitinol is used in self-expanding stands and orthodontic wires. In aerospace, it's used for actuators that change wing shape. And in robotics, it works as an artificial muscle in compact, silent mechanism. Nitinol's microstructure. Nitinol has two phases, martensite, which is soft at low temperatures, and austenite, which is stiff at high temperatures. It can switch between these phases with heat or stress, allowing it to behave smartly. Next is shape memory effect. In the martensite phases, Nitinol can be bent. When heated, it returns to its original shape as it changes back to austenite. This is called the shape memory effect. Superelasticity. In the austenite phases, Nitinol stretches and forms martensite. Once the force is removed, it snaps back to shape, enabling large, reversible deformation without damage. Next is biocompatibility and fatigue resistance. Nitinol is safe inside the body, resists corrosion, and lasts through millions of cycles, making it ideal for medical devices like stents. This graph illustrates the superelastic behavior of Nitinol. On the blue curve, you can see how the material stretches, not in a straight line but through a plateau region where the stress-induced martensite is forming. Then, when the stress is removed, it follows the red dashed line, returning to its original shape. This creates a reversible, non-linear loop, which is a key feature of superelasticity. This allows Nitinol to work like a spring without a motor, ideal for compact systems like robotic actuators and durable eyeglass frames. This diagram shows the phase transformation mechanism that powers Nitinol's shape memory effect. On the left, we have twine martensite, which becomes detwined under stress. Then, with heating, it transforms into the austenite phase, which is stronger and returns to the original shape. When cooled again, it returns to martensite. This complete cycle allows the material to remember and recover its shapes, making Nitinol one of the most powerful smart materials in engineering today. Thanks to its smart properties, Nitinol is used in many innovative applications. In the medical industry, it's used in stents that expand automatically inside the body, responding to temperature. Orthodontic wires made of Nitinol apply continuous, gentle pressure. In aerospace, Nitinol actuators help control flaps and wing shapes, replacing traditional mechanical systems, reducing weight and improving energy efficiency. In robotics and electronics, Nitinol serves as a compact actuator, acting like a muscle that contracts when heated. This innovation shows how Nitinol simplifies design, lowers energy use, and supports sustainability goals. I believe Nitinol should be further developed and widely adopted in future technologies. First, it offers multifunctional behavior in a single material, like shape change, actuation, and elasticity. Second, it works without motors or gears, making system lighter and quieter. Third, it's biocompatible and corrosion resistant, which is especially important in long-term medical applications. To expand its use, improvement could include increasing fatigue life, lowering production costs, and integrating Nitinol with electronic controls for smarter systems. It is especially promising in wearable tech, soft robotics and smart prosthetics. Looking ahead, smart materials like Nitinol are expected to play a major role across industries. The global market for smart material is growing rapidly, which is projected to reach nearly $100 billion by 2032. We will see more integration with AI system, enabling smart implants that adjust in real time, clothing that changes shape or stiffness, and IoT devices powered by energy harvesting Nitinol actuators. These materials will enable smarter, more adaptive and more sustainable engineering designs in healthcare, aerospace, construction and more. In conclusion, smart materials are a key innovation in material science. Nitinol stands out for its ability to transform based on temperature and stress, which offering both shape recovery and super elasticity. These properties are made possible by its unique structure and they support applications in robotics, medicine and aerospace. With further development, Nitinol can help solve real-world engineering problems by making systems lighter, more efficient and more intelligent. Okay, that's all for now. Thank you for watching. I'm Fahrul Nazhan Syahmi and this concludes my presentation.